So when we're dealing with difference in population proportions, remember that we're constructing a new distribution. In this new distribution, we're interested in finding the mean and standard deviation or standard error of that new distribution. In previous set of equations, highlighted the following key statistical principle. What is that principle? The mean of all differences. The mean of all differences is the difference of the means. So when we are constructing this new distribution has a mean, has a balancing point, has a center. But what is that mean? Remember, we had two distributions. We found the difference between them and we constructed a new distribution. In this new distribution, the mean or the center is equal to the mean of the first distribution minus the mean of the second distribution. Remember that we are dealing with proportions. So we find the center of the first distribution, we find the center of the second distribution, do the subtraction between them. That's how we get our mean. So the formula for the mean is not that complicated. Estimated standard error of differences in sample proportion. Well, this formula has square root, then inside square root, we have some multiplication, subtraction, division. The estimated standard error of differences in sample proportions is based on the sample proportions PM hat and PB hat. And the formula for that to help us find standard error is, so we're finding the standard error. This is the square root of P sub M hat times 1 minus PM hat divided by N sub M. What is N sub M? It's the first sample size. So N sub M is the first sample size. Plus, after calculating this number, we add that number to the second one, which is PB hat times 1 minus PB hat divided by N sub B. What is N sub B? It's the second sample size. Okay, remember that we're interested in constructing the confidence interval. We have our standard error. The next step is to form the margin of error. The margin of error follows formula Z sub C, which is our critical value, times this square root, which is our standard error. Recall that the margin of error E for any normally distributed unbiased estimate of population parameter is E equal to Z sub C times the standard error. So we found the mean, we found the standard error. The next step is to find the margin of error. Okay. This is our margin of error, ZC. ZC depends on the level of confidence. In this formula, Z sub C is the standard normal critical value. It corresponds to a level of confidence. The table below, which you have seen in previous lessons, summarize the most common confidence levels and their critical values. So if the question says, hey, you have 90% level of confidence, Z sub C, or the critical value that you're going to use to form your margin of error, is 1.645. If the question says, hey, I'm going to change the level of confidence to 95%, then the critical value associated to that level of confidence is 1.960. So if the question says, hey, construct a confidence interval, but with 95% level of confidence in the margin of error formula, we're going to use 1.960. But if the question says, hey, now I'm going to change the level of confidence to 99%, ZC is going to be 2.576. What's the meaning of that? It means that when you're trying to construct the margin of error, your critical value is not 1.645. It's not 1.960. It is now 2.576. So in each question, our job as a statistician is to identify the level of confidence. Based on that, we can use the proper critical value. Very well, let's see what do we have in the next page. Using the estimated standard error formula above, the margin of error now becomes E equals to Z sub C times the standard error, which you remember follows square root of PM hat, 1 minus PM hat, and is dropped, divided by N sub M plus PB hat, 1 minus PB hat, divided by N sub B. Now, to form the confidence interval, we need our best estimator minus the margin of error and best estimator plus the margin of error. But what is that estimator? So the confidence interval is equal to point estimate minus margin of error, comma, the point estimate plus the margin of error. So in previous lessons, we learned that if we have just one distribution, just dependent on one set of data, then the point estimator for proportion was P hat, the sample proportion. And when we're dealing with the mean, for mean, we used X bar, which was the sample mean. So one distribution, point estimator, for proportion P hat, for the mean, we use X bar, the sample mean. Note that here we found the difference between two distributions. So in this case, the point estimate depends on both of those distributions. It means that your point estimate is the proportion of the first sample minus the proportion of the second sample. And remember that to construct the confidence interval, we have point estimate minus margin of error, comma, our point estimate, which is the difference between proportions of two samples plus margin of error. So we add the margin of error here. This is how we get our confidence interval for difference in proportions. In each of these cases, PM hat minus PB hat is our point estimate. PM hat minus PB hat, point estimate, minus the margin of error, plus the margin of error. Well, give us an example. Okay, let's take a look at this example here. In question 1, you identified representative sample proportions from the individual sampling distributions of sample proportions. Let's use these values to construct a 95% confidence interval. So this is an important piece of information. The confidence level is 95%. So if I get back to the table that I had before, 95% confidence level, critical value is 1.960. 1.960. This is a piece of information that we use our table to drive the information from. Okay. Confidence interval for the difference in population proportions, PM minus PB. Guys, note that we are not using sample proportion. We're using population proportion. That's why you don't see any hat on top of P. Very well. Use the values for PM hat and PB hat for question 1, and sample sizes. Okay, sample sizes are given to us. N sub M is 65 for millennials, and NB, the second sample size, is 50. You need this information. Okay, we'll plug all of them into the formula and then calculate. So this is N sub. Calculate the estimated standard error of differences. Well, okay. We know that the standard error follows square root of PM hat times 1 minus PM hat divided by NM. Remember that from previous pages, we had PM hat as almost 60%. So 1 minus 60%. Remember, we use just approximation. N sub M is 65 plus. Then PB hat, it was about 35%. 1 minus 35%. Divided by N sub B, or the second sample size, which is 50. If we use our calculator, it approximately gives us S of E approximately 0.090. This is our standard error. in our next step, we need to find margin of error. Margin of error is equal to ZC times S of E. ZC is critical value related to level of confidence. Well, the level of confidence is 95%, but the critical value that we're going to use for our formula is not 95%. Make sure you're using correct critical value, which is 1.960. 1.960 times S of E. We just calculated S of E. So the approximation is 0.090. So our margin of error is going to be 0.178. Well, now that we have the margin of error, we can quickly construct our confidence interval. Margin of error 178. So the confidence interval was point estimate minus the margin of error. So point estimate, this is our lower limit, minus the margin of error, and point estimate, this is our upper limit, plus the margin of error. But what is our point estimate here? We need our P sub M hat and P sub B hat that we calculated before. It is 0.24 minus 0.178 and 0.24 plus 0.178. So our confidence interval is going to be 0.062 and 0.418. So what's the meaning of that? It means that we are 95% confident that the difference in proportions of millennials and baby boomers who rely on Facebook as a source for news is between 6.2% and 41.8%. Very well, let us move on to the next page. Question 4. Each difference in sample proportions will lead to a different interval estimate. Of course, we know that. Sometimes there are extreme cases of confidence intervals that do not contain the difference in population proportions. So sometimes you construct a confidence interval and the difference in population proportions is not included in that confidence interval. So as a statistician, what is the solution to that? Remember that our goal is to find a collection of data that captures the true population parameter. In this case, we are working with population proportions. So we're expecting to get population proportions included in those confidence intervals. To create an extreme case of a confidence interval, pick extreme values from PM hat and PB hat and create the corresponding 99% confidence interval. So to make sure our confidence interval contains the true population proportion, what we're going to do, we're going to create an extreme case. What is that extreme case? It's the case that you're constructing a confidence interval using extreme values of PM hat and PB hat and create 99% confidence interval. Take a look at our distributions here. So question says, from the dot plot of proportions of millennials who used Facebook, pick the largest of the simulated sample proportions. Okay, the largest proportion on the horizontal axis, it seems like it is 73%. So this number here is 73%. We're going to do the same thing for the second distribution. For this distribution that is skewed to the left, this distribution is skewed to the left because the tail is on the left, and this distribution is skewed to the right because the tail is on the right. So we pick the smallest value. For the first distribution, we pick the largest value. For the second distribution, we're going to pick the smallest proportion. So it seems like the smallest proportion here is 23%. 23%. Okay, now we can find the difference between these two values. PM hat minus PB hat is 73% minus 23%, which is 50%. Now we're going to repeat the same process. We're going to find the standard error. Then we're going to find the confidence interval for 99%. And then it gives us the extreme case. So standard error is equal to square root of, well, PM hat (73%), 1 minus 73%, divided, we haven't changed the sample sizes, so we're going to use what we had before, plus 23, 1 minus 0.23, divided by 50. Our standard error is approximately 0.081. Now we need to find the margin of error, ZC. Remember that we are working with 99% confidence interval. In that case, the critical value, if we check our table, is 2.576. We multiply that critical value by the standard error, which is 0.081, and the margin of error is going to be approximately 0.209. So what is important for us? The margin of error is important here. Remember that our point estimate, the difference between these two proportions is 50%. So we can quickly construct the confidence interval. 50% minus 20.9% and 50% plus 20.9%. So our confidence interval is 0.291 and 0.709. Let us just quickly compare this information, this new information, and what we did before. This is our previous calculation. Our previous calculation was, okay, 6% to 41%. 6% to 41%. This new confidence interval is 29% to 70.9%. As you can see, the information that we just gained are shifted to the right-hand side. It doesn't contain the 6%. So it doesn't contain the confidence interval, some part of it, that we calculated before in this new one. So our conclusion is, we found that the most extreme values of PM hat minus PB hat generates a confidence interval that does not contain the difference in population proportions.